Hello everyone, and welcome to the lecture on dynamic arrays. Let's go ahead and get started. In this lecture we're going to learn what is a dynamic array, and we're also going to learn how to implement a dynamic array. So let's just discuss what a dynamic array is. When you're building out a list in Python, you may have noticed that you don't actually need to specify how large the array or that list is beforehand. So for instance, here we have a little diagram that we saw earlier of all the bytes that are allocated to a particular array. But in Python, these lists are dynamic, so you don't need to specify how large your list is going to be beforehand. You can just keep constantly adding to it. So how does Python actually do this? Well, it does this through the use of dynamic arrays. So that list instance actually often has a greater capacity than its current length. So if you put in a list with 3 elements in it, usually that list is going to actually have a greater capacity to hold more elements than just the 3 you initiated it with. But if you keep adding elements to it or keep appending elements to that list, eventually even that extra space is going to run out. So what we're going to do is show a live coding example that really demonstrates the relationship between the size and bytes allocated to a list or array and the actual length of the elements in the array. So let's go ahead and jump to the Jupyter Notebook and show you an example of this. So here we are at the Jupyter Notebook, and let's go ahead and go over some code that I wrote out in order to experiment and explore the relationship between this list's length and the underlying size that the computer's holding in memory. So first thing I did was I just imported SYS, the system, and that's going to allow us to use a getSizeOf function, which will let us know the actual size in bytes that the computer is holding in memory. After that, I just set an arbitrary n, and that's going to be the amount of elements in the array. And then I set an empty list called data, and then we're going to say for I in range of n, set a equal to the length of data, so that's going to tell us the number of elements in that list. And then we're going to set b equal to sys.getSizeOfData. And that's going to tell us the actual size in bytes. And then we're going to print out the format to say length, which is going to report back how many elements are in that list. And then we're going to see size in bytes. And we're going to format or use print formatting to print that out. And then after that, I'm going to increase the length by 1 by just appending that particular number or integer to the list. So let's go ahead and run this and see what happens. Right now we're running it for n equal to 10. I'm going to zoom out a bit so we can see the various print statements. Here we go. So you notice we begin with a length of 0, and we have size in bytes is 64 bytes are being used. Now here's where the interesting part happens. When we increase length to 1, the size in bytes gets increased to 96. But you notice as we keep increasing length all the way up to 4, the size in bytes doesn't actually change. So what Python has done is it's actually set a number of bytes larger than what it needs to hold the current elements in the list while it's appending new elements to the array. So to get a better idea of this, we're going to actually put in a much larger n. So let's go ahead and put in, let's say 50 and run this. Okay, so you'll notice a pattern here. Basically, as we keep adding elements to the arrays, the size in bytes that the list is using increases. But you'll notice it happens in chunks. So for the first element, we have 64 bytes. Let's go ahead and zoom in on that. And then for the next 4 additional elements, we have 96 bytes. So the first element has 64, the next additional 4 have 96 bytes. And then the next 4 have 128 bytes allocated in memory. And then we have 192 for a larger section of the next bytes. And then 264 for a larger section, and then 344, 432, etc. So you'll notice that as we keep adding elements, basically what Python is doing is it's grabbing more and more real estate in memory. And it's allowing us to see that there isn't an underlying change in memory when you insert more and more elements until you need a memory usage jump. So for instance, back here, if we look at the 5th element, size in bytes 128, we can see that we needed to make a memory usage jump. So a basic analogy to this system could be almost like a hermit crab grabbing larger and larger shells. So this list is grabbing more and more space in memory until it realizes, hey, I'm growing large enough that I'm probably going to need more in the future, and then it grabs more memory. But it does it in chunks so that it doesn't need to constantly do it for every element that gets appended to it. So even if you just add one element after the first element, it'll still grab 96 bytes, which is going to be able to hold those next four elements, 1, 2, 3, and 4. And then when you add the fifth element, it's going to jump to 128, and that's going to be able to hold future elements as well. And it's going to keep doing these jumps almost like a hermit crab, jumping to a larger shell until it grows large enough that it's going to need to jump to another shell. All right, so let's go ahead and go back to the presentation to finish off some of the theory of this. All right, so now at the presentation, what we're going to do is just briefly describe how to implement a dynamic array. And then in the next lecture, we'll actually live code an implementation out. So the Python list class provides a very optimized implementation of dynamic arrays, which we're going to rely on for the remainder of this course. But just for as an instruction, we're going to make our own basic implementation. So let's go ahead and learn the theory behind how we're going to implement this. And then in the next lecture, we'll actually code it out live. So the key is to provide a means to grow the array. Let's say in this case it's A. So we want to grow the array A that stores the elements of a list. And of course we can't actually grow that array because we already know that it needs to have a fixed capacity. So if an element is appended to a list at a time when the underlying array is full, we're going to perform some steps. And let's go ahead and see what those look like. So the steps are going to be, first we allocate a new array, let's call it B, with a larger capacity. And then we set the indices, let's say B of I equal to A of I, for I all the way from 0 to n minus 1, where n denotes the current number of items. And the reason we are using n minus 1 is because the index starts at 0. And then what we're going to do is say set A equal to B, and then henceforth we're going to use B as the array supporting the list. And then finally we're going to insert that new element n into the new array. So let's go ahead and see an illustration of this process so it's a little more clear. All right, so again, here what we have is an array, A. So we have this array A. We allocate a new array B that has a larger capacity. So that was the bytes, that new chunk of bytes that we saw when we were actually programming out that print statement. So here we have this array A. It already has references. We allocate a new chunk of memory space, and we'll call that array B. And then we set the references here on storing elements of A and B. And then finally we reference the array B. Now it's array A. So again, the steps are we create this new array B, store the elements of A and B through a reassignment of the reference, and then we call the B array, now it's A, so now we have this new array. And that information or that memory space that was allocated to the old array can now be used. What we're not showing here in this diagram is what's called garbage collection of the old array or the insertion of the new element. We'll go over those in a future lecture. Now, the last remaining issue is to consider how large of a new array to create. A commonly used rule is for the new array to have twice the capacity of the existing array that has just been filled. And later on, we'll actually have a lecture that's describing the mathematical analysis to justify that decision. And so just to go over that again, we want to learn how large of a new array to create. That common rule is twice the capacity of the existing array, and later on we'll see mathematical reasoning behind this. So just to review what we've done, we learned what a dynamic array is. We saw theoretically how to implement a dynamic array, and we also saw some live coding on the thought process and just what's actually happening under the hood, so to speak, where we're appending new elements, but we can see that there's these chunks of bytes in memory that are being allocated as we create new arrays. All right, so up next, we're going to code our own implementation example of a dynamic array. All right, thanks everyone, and I'll see you at the next lecture.